This is a new series of lecturelets that I'm going to give, all focused on matrix analysis and with particular focus on least squares fitting and eigendecomposition as it is used for spatial filtering. So this is really all about linear algebra matrix analysis. So what is linear algebra? Linear algebra is a way of describing and working with vectors and matrices, linear operations, least squares projections, and eigendecomposition. So these are all the main topics that I hope to cover in the next several lectures. If you've taken a course on linear algebra, you might recognize these as being, the main topics that you would study in a semester-long course on linear algebra. And this is not going to be a semester-long set of lectures. So there's a little bit of a departure from all the other lectures in the sense that with the time frequency analysis lectures, the goal is for you to understand every little mathematical detail and every MATLAB implementation of how all these time frequency analysis methods work. Here with the matrix analysis lectures, I hope to give you more of a conceptual overview. There are some things like, for example, matrix multiplication, which I think is nice for you to know, but I'm not going to go into all the details. And of course, to really gain a lot of familiarity and expertise with, for example, eigendecomposition, you would have to spend quite some time focusing, doing a lot of problems and things to really crystallize your knowledge of linear algebra. So I hope, or my goal here is to get you to understand these operations conceptually enough, well enough, in order to be able to use them in MATLAB. And you'll have to do a little bit more work on your own if you want to, be able to compute an eigendecomposition by hand, for example. So what is linear algebra? It's useful to think about an analogy. So if you go from arithmetic to algebra, so arithmetic would be like 2 plus 3 equals 5, and algebra would be 2 plus x equals 5, and then you solve for x. So in this way that arithmetic is to algebra, you can think of algebra as being to linear algebra. So linear algebra is much more open. It's much more multidimensional and more flexible. Linear algebra gives you many dimensions. There's no sort of cap on the number of dimensions that you can have. Interestingly and importantly, linear algebra, the dimensions are typically not Cartesian. So you think about your typical two-dimensional space, the xy plane, the Cartesian plane. The two axes are orthogonal to each other, but usually in linear algebra, these dimensions are not orthogonal to each other, and there can be many advantages for that. The interesting thing is that linear transformations can generally be represented as or implemented as a matrix multiplication. And for this reason, people often use the terms linear algebra and matrix algebra fairly interchangeably. In general, when people use the term linear algebra, they're indicating more of a focus on theory and proofs, so it might be a little bit more abstract. And when people say matrix algebra, usually it's more with a focus on specific applications in science. And so actually this set of lectures is probably better called matrix algebra than linear algebra. So why is it important to know something about how to work with matrices and how to use matrix operations in electrophysiology? In part, the answer is obvious because, almost all of our data are stored in matrices. So you can think of EEG data as being channels by time matrix, or maybe it's three-dimensional if you also have trials in there, if you epoch out the continuous data into trial data. And there's all sorts of things that we like to do with our data that are actually done through matrix analysis procedures, including principal components analysis, independent components analysis, source localization, spatial filtering, and statistics, and this is not an exhaustive list. And here, so in this set of lectures, we're going to be talking about PCA, we're going to be talking about some mechanisms of spatial filtering, and we'll be talking a little bit about statistics. And there are other procedures that use matrix analysis. So data cleaning, I guess that's also related to ICA. Dimensionality is related to spatial filtering. Least squares fitting is one implementation or one sort of mechanism of doing statistics. So these are the kinds of things that we are going to be learning about. So, but before we get to the really fancy stuff with matrices, we have to go back to the beginning and make sure we understand the fundamental rules for working with vectors and matrices. And this is the main focus of this lecture. Some of these slides and these concepts are a review that I introduced you to many lectures ago towards the beginning of this lecture series, but it's good to have a bit of a review here. It makes the whole package complete. So what's a vector? So many concepts in linear algebra can be implemented or understood either in an algebraic sense or in a geometric sense, and in different situations it's useful to have to understand these different interpretations. So here's the algebraic interpretation of a vector. It's simply an ordered list of numbers. So here we have a list of numbers, 1, 2. We can call this a two-dimensional vector or a two-element vector because, of course, it has two elements. Now, I'm sure you already know the geometric interpretation of a vector, and that is just a point in space given by the coordinates 1, 2. So we go over 1 and up 2, and this gives us our point. And now we push this a little bit further, and we think about this vector not just being a coordinate in space, but as being a line that's drawn from the origin to the point specified by those coordinates. Now, this line doesn't have to start at the origin. It could start anywhere in space. It just needs to go 1 unit over and 2 units up. Nonetheless, it's convenient to think about vectors as starting from the origin, and for the rest of this lecture series, we're only going to be thinking about vectors starting at the origin. Okay, so that was a two-dimensional vector. Now we get to a three-dimensional vector. It's exactly the same concept. You just add another element to the series of numbers. So here we have our sort of numeric interpretation of a vector, and now here we go. This is our three-dimensional axis. So you can see it's still the same concept. We still have a point in space, and we think of this vector as being a line that goes from the origin to the point specified by those coordinates. So 3 coordinates, three-dimensional space. That's very simple. Now the concept is exactly the same for any number of dimensions, any integer number of dimensions, I should say. So you can have like 1,000-dimensional vector, and you can imagine this is where the geometry really stops being useful. But for this reason, many concepts in linear algebra are first introduced in 2 dimensions, or sometimes 3 dimensions when necessary. And then the goal is to understand conceptually what's happening in 2 dimensions. Everything else for higher dimensions is exactly the same. It's just very hard to visualize. So, for example, we will be doing things in 64-dimensional space because our sample data have 64 channels, and each channel corresponds to a dimension. But same concept. Okay, so what can we do with vectors? We can add vectors, and we can scalar multiply vectors. So adding vectors is very simple. You have 2 vectors, and if you want to add them together, so here x plus y, vector x plus vector y, you simply add together all the individual components. So the resulting vector would be 3 and 8 and minus 4 and so on. You can see here that vector addition only works when the 2 vectors have exactly the same number of elements. So this is a 5-dimensional vector. If this only had 4 numbers in here, it would not be possible to add these 2 vectors. So it's not always possible to add any 2 random vectors. So the next operation is scalar multiplication. That was this one. So if c is a scalar, a single number, then the scalar multiplication of c times vector x is simply multiplying each element in x by this scalar c, this single number. Good. So why do we call this scalar multiplication, and why do we call this a scalar instead of a single number? That will make a lot of sense when we consider the geometric interpretation of scalar multiplication. Here's this thing. I don't know why the animation is a bit backwards. Anyway. So this is the algebraic interpretation of addition and scalar multiplication, and here we have the geometric interpretation. So let's do scalar multiplication first, because that one's a bit easier. So scalar multiplication means you take a vector, and then when you scalar multiply that vector, you get a new vector which is pointing in the same direction. So if you imagine that there's like this infinitely long line that goes here. Now the scalar multiplication of this vector v stays on somewhere on this really long line. It just changes this vector by a little bit. So it stretches it out or it compresses it if the scalar, so in other words, it's scaling it. That's why they call it a scalar. And if this scalar c is negative, it still stays on this line, but then it points in the other direction. So if the scalar would be -1, this vector would be pointing over like this. Okay, so now we do vector addition. So now if here is our, this would be vector 1 and vector 2. If we were to add these two vectors together, the geometric interpretation is that you take this vector, you take one vector, and you slide it up so that the start of this vector is at the end of this other vector. So now you can see I've just like transposed this vector up here. And remember I said earlier that, actually I said we're only ever going to consider vectors that start at the origin, so that's already wrong, but that's okay. So this vector and this vector are the same vector, they're just translated up. And now you put one vector at the head of the other vector, and then the line that goes from the origin, or from the start of the first vector, all the way to the end of the second vector, that is the new vector. So this is vector v1 plus v2. And this works both ways. I could have also taken this vector and put it at the end of this vector, and you can already see, and you can confirm in MATLAB later, if you like, that that's going to produce the same vector. All right, so that's about addition and scalar multiplication, but those are not the only things that we can do with vectors. We can also compute things called the inner product and the outer product. The inner product is more commonly known as the dot product, and again, the dot product is a concept that's incredibly important in signal processing, and you've seen it with Fourier transform and with convolution, and now now here we're going to discuss it again. So to compute the inner product in a linear algebra sense, what you want to do is start with these two vectors as column vectors, and then transpose one, which means flip it on its side. We'll talk more about transposing later. And then compute something called a matrix multiplication between x transpose and y. And matrix multiplication we'll talk about a little bit later, but generally the way it works is, so this would give you the transpose of x, and here is the column vector y. And to compute this matrix multiplication, what you want to do is pointwise multiply, and then sum as you're moving along. So you start 1 times 2, plus 0 times 8, plus 2 times -6, plus 5 times 1, plus -2 times 0. So you have to sort of imagine going on one vector over and the other vector down simultaneously. And as you're going over and down, you're also doing pointwise multiplication and summing. Of course, this is exactly the same definition of the dot product that we discussed in previous lectures. It's just thinking about the operation in a slightly different way. So the answer here is -5. And you already know that the dot product between two vectors is just a single number. So that's the dot product or the inner product. There's another way to multiply two vectors, which is produces something called the outer product. Now the outer product works the other way. So we want to transpose not x, but y. So now we have a column vector times a row vector. And now we're still doing matrix multiplication, so it still works in the same way. We go over here and then down on this vector. But now there's only, like, it can only go over 1 unit and it can only go down 1 unit. So we end up with a full matrix. So the outer product between these two vectors would look something like this. And the interesting thing about the outer product is you can see that each column is just a scaled version of this column. And the scaling factor is given by each element in the second vector in the row vector. So this is, well, 1 times this column is this, and then 0 times this, of course, is 0, and so on. And you can also see this the other way around. So you can say that each row in the outer product is a scaled version of this row vector, and the scaling coefficient is given from the column vector. So this is, the first row is 2 times this row vector, and then the next one is 8 times this row vector, and so on. In practice, we're not going to be using the outer product for the rest of these lectures. The reason why I highlight this and show this to you is that it happens sometimes in MATLAB that you're trying to compute the dot product, the inner product, and you're expecting a single number, but instead you end up with a full matrix. And so if you see that situation, you don't have to freak out. You don't have to think that MATLAB is possessed and is doing something wrong. The most likely explanation is that you are computing the outer product instead. So this is just something in MATLAB. It's a easy to make mistake that you have to look out for. It's also easy to make because this formulation versus the matrix formulation for the inner product, these depend on the vectors being column vectors. So in fact, if your vectors were row vectors, this would give you the outer product. And if these were row vectors, this would give you the inner product. So it can get a bit confusing. The point is, don't be alarmed if you see a full matrix when you're expecting a single number. You probably just computed the outer product. So here's by way of summarizing this. So we have a row vector times a column vector, and that gives us a dot product. It's a single number. And if we flip the orientation, then we get a column vector times a row vector, and that gives us the outer product. So just a visual summary. Oh yeah, so now the next thing I'd like to introduce you to is matrix addition and matrix scalar multiplication. This is also fairly straightforward. Matrix addition is basically, it works the way you would expect it to work. So if you have two matrices and you sum them together, the resulting matrix has the same size, the same number of rows and columns, and each element is just the summation of the corresponding elements in these two matrices. So the upper right element in the sum matrix resulting from the addition of these two matrices will be -8 because it's this guy plus this guy. So, and similar to vector addition, this matrix addition is defined only for two matrices that have exactly the same number of rows and exactly the same number of columns. So the matrices have to be the same size. Scalar multiplication is also very simple. It's what you would intuitively expect it to be. So we have a matrix and a scalar that's a single number. And so the result of this is going to be this scalar, this single number, multiplied by each individual element in the matrix. So I think I didn't feel like drawing that out because I didn't want to get all the C's in there. So anyway, that's matrix addition and scalar multiplication. And now we get to matrix multiplication, which is a bit more complicated. It's a bit more involved. And I'm not going to go through all the mechanics of matrix multiplication here. To implement matrix multiplication, you just perform a series of dot products, like with the inner product. So it's like you're computing the inner product between each row in the left matrix and each column in the right matrix. If you're curious to know about the details, you can look those up online. But what I would like you to know here is the rules for matrix multiplication, because matrix multiplication is not like normal multiplication with individual numbers. You can multiply any two numbers, and it's commutative in the sense that a times b is the same thing as b times a. So 3 times 5 is the same thing as 5 times 3. But with matrices, things are the rules are totally different. It's a very different operation. And this is what I would like you to know. So if you have two matrices that are m by n and n by k, then the matrix multiplication between these two matrices is defined, it's permitted, only when the inner dimensions match. So when the rows in the left matrix have the same number of elements as the columns of the right matrix. And then the size of the resulting matrix is going to correspond to the outer dimension. So here we have m by n and n by k. So these are the two inner dimensions and they match. So matrix multiplication is defined here. And here we have the outer dimensions are m by k, and that defines the size of the new product matrix. So I know it's a little bit confusing. If this is the first time you're being introduced to matrix multiplication, it may seem a little bit weird. But if you spend some time thinking about or working through the mechanics about how matrix multiplication is implemented as a series of dot products between rows here and columns here, then it actually does make a lot of sense, and this is the only way it can work out. All right, so matrices have sizes, and they're generally referred to as m by n, or rows by columns. And it's important to remember that we refer to matrix sizes as rows by columns and not columns by rows. There's no inherent meaning why it has to be rows first and then columns. It's just that this has become the standard formula in linear algebra, and so you have to use this formula in order to understand why, or in order to follow a lot of other concepts in linear algebra. So how do you remember that it's always m rows by n columns? One way to remember is this with this mnemonic, Mr. Nice Guy. So here we have m rows and n columns. So that's an easy way to remember how to think about matrix sizes. So this is a 1 by 4 matrix because there are m rows, so there's one row and 4 columns. So this is also called a row vector. Before I was calling it a row vector, but actually now you can appreciate that a vector is really just a special case of a matrix where the number of elements on one dimension is 1. So here we have a column vector. This is a 3 by 1, so m rows and n columns. So it's a 3 by 1 matrix. So in here we have a full matrix. This is 3 by 4. It's m rows and n columns, so 3 by 4. Now I would like to give you a bit of a warning about how indexing works in MATLAB. And you may have come across this before, but I want to make it explicit here. Because it can be a useful and powerful way to index matrices in MATLAB, but it can also be a source of confusion, and it's also a source of the worst type of MATLAB error you can make, because you can do something wrong without MATLAB actually giving you red text. So here we have a 3 by 4 matrix, and these coordinates are how you would refer to elements inside a matrix. So this is 2, 3. That means it's the second row and the third column. But in MATLAB, you can also index each of these elements using just a single number. And the way that MATLAB numbers elements in matrices is going down the column. So this is 1, 2, 3, and then this is actually element number 4 in the matrix. Because it's the first element in second column. So you can see why this gets confusing, because this is a 3 by 4 matrix, but you can get up to element 12. So when you look at this picture, it may seem pretty obvious, and you might not get very confused with this kind of a matrix. But we'll see in MATLAB in a few minutes a situation where it's easy to get very confused and basically to have no idea where in the matrix you are, even though you're doing some legal indexing operation. All right, so let's take a look at some of these concepts in MATLAB. Most of this code actually is just going to draw some figures that you just saw in the PowerPoint screen. So most of going through this code is really just about you gaining familiarity with the plotting commands and so forth. So here we have this 2-element vector, and here we have this 3-element vector, and you can click and drag this around, and maybe it's easier to see how this vector fits into this 3-dimensional space. Here's a little code about vector addition. So you can see this is the same thing that we did, the same image that I showed in the PowerPoint. And so you can see that to get this red line, you just imagine taking this black line and shifting it up so that it starts not at the origin, but at the end of this blue vector, and then you would get this red vector here. So you can take a few minutes to try playing around with these different numbers and get a bit more of a intuitive geometrical sense of what it means to add 2 vectors. And here we are with our scalar multiplication. And again, the important concept here is that scalar multiplication involves just a scaling of this vector. It's not pointing off in any other direction. You can see like these 3 vectors are all kind of pointing off in their own directions. But with scalar multiplication, we're not changing the direction of the vector. We're just making it longer or shorter, or maybe point in the opposite direction. Maybe it seems trivial that I'm continuing to stress this concept, but this idea here about scalar multiplication of vectors is an important concept for understanding eigendecomposition, which is the basis for principal components analysis. It's the basis for a lot of different kinds of spatial filtering and component-based analyses that we're going to talk about in a few lectures. So make sure you have a good feeling for what this concept means. All right, so here we do some matrix addition and scalar multiplication. And well, you can run through this code. You can see it produces an error. So you can try to figure out which line is producing an error and why you get that error and how to fix that error. This is more rules for matrix multiplication, and this was the concept about to implement matrix for matrix multiplication to be implemented, the inner dimensions have to match, and the outer dimensions define the size of the product matrix. So again, we get a nice friendly MATLAB error here. So you can figure out which of these 2 operations is valid and which one produces an error, and then you can see if you can fix it. I also encourage you to, you can also try playing around with matrix C and figure out from all the possibilities of multiplying these 3 matrices, which ones are valid and which ones are invalid. So here we have some code to illustrate the idea of matrix indexing and finding your way around matrices. So here I created this matrix that looks like, this is like the linear indexing that MATLAB would do. So here now we want to index the element in A that's at row 3 in column 2. So you can see here, that's row 3 and column 2, so it's number 6. And then, you can try that indexing the 6th element also gives you 6. And this might initially feel weird to do something like to write code like this, because this is just a 3x4 matrix. There is no dimension that has 6 elements, but this is a legal thing to do. So here's where you get a situation where this can be really difficult. Imagine we have this, what is this, 5-dimensional matrix. And now if you want to, so this could be a real size of a matrix, right? It could be results of a time frequency analysis. This could be channels by conditions, by frequencies, by time, by, I don't know, analysis type or something. So now let's say we want to get the value of this channel and this condition and this frequency and so forth. This is a very intuitive way to do this. Now, this is also technically possible. You can just access the 582nd element in this matrix. Now, if you would ask me where this is inside this matrix B, I have no idea. I mean, there's ways to find out, of course. But the point is that this is a very intuitive and sensible way to index matrices, and it's unlikely to produce errors. And this is possible, but just asking for trouble. So I do not recommend intentionally accessing matrices this way. Better to do it this way. The rule of thumb for indexing matrices, and I say this because I see many students make this mistake, and again, this is the worst kind of MATLAB mistake you can make, because this is legal, but it might give you the wrong answer. So the rule is, when you're trying to index a matrix, however many dimensions the matrix has, when indexing you need n-1 commas. So here we have matrix A. This is a very simple case. So it's a 2-dimensional matrix. So whenever we're indexing something inside the matrix, we need to have 2 minus 1 commas. So we need to have 1 comma. And that's what you see here. So this is, I think, the best way to index this matrix, because we have 1 comma. And here, again, this is a bit longer code, right? Because we're accessing multiple elements inside each dimension, but that's okay. We still have 2 dimensions and 1 comma. So now we know that this is going to be a good way to access this. Good. So there's a few more things I would like to cover in this lecture in order to prepare for the next lecture. There's different types of matrices, and different matrices, there are a few special kinds of matrices, and these special kinds of matrices are given specific names so we can refer to them easily. So square matrix, this is pretty obvious. It's a matrix that has the same number of rows and columns. So this is a 4x4 matrix. It's a square matrix. If a matrix is not square, it's called rectangular. So a 3x4 matrix would be a rectangular matrix. Then there's also something called the diagonal, which is these elements that I've outlined in white here. So the diagonal is, well, it's pretty obvious what it is. It's just the elements along the diagonal of the matrix. All these other elements are called the off diagonals. So that's a square matrix. There are certain types of square matrices, which are called symmetric matrices. And a symmetric matrix is very nice because it has the elements are identical to the upper right and lower left of the diagonal. So it would be like if you imagine this is a piece of paper and you fold it along from the top left corner to the lower right corner, and you like fold it down, and you would see that there's symmetry. These are the same elements. In fact, there is an error in this matrix somewhere. So you can see if you can find the error and then figure out why you know that it's an error, given that I said it's a symmetric matrix. All right. And now there's another special type of square matrix, which is also symmetric. And this is called the identity matrix. And the identity matrix is all ones on the diagonal and all zeros on the off diagonal. The identity matrix is a very important matrix because because it's like the neutral matrix. It's the matrix that you can multiply by any other matrix or any vector, and it gives you back the same matrix or the same vector. It's the equivalent of the number 1, so you can multiply 1 by any other number and you just end up with that other number. So the identity matrix times any other matrix is just that other matrix. Okay, so now we're going to talk about the transpose. Transposing vectors is pretty straightforward. You just take a column vector and you like rotate it so it becomes a row vector. So the transpose of this vector, you can see it's just it's just been rotated. So and then we can transpose it again, and not surprisingly, it gives you the same matrix back. So that's pretty intuitive. The transpose turns out to be important for a number of linear algebra operations, including the inner product and outer product, which you've already seen. And when we talk about least squares, then the transpose becomes very important. So that's transposing vectors. Transposing matrices is the same concept, except now the matrix is a little bit bigger. So the transpose of this 2 by 3 matrix is this 3 by 2 matrix. And you can see, so there's two ways to interpret this matrix transpose. You can say that each row has turned into each column. So now the first row turned into the first column, the second row turned into the second column. Or you can see that the columns here turn into rows here. So this is the first column, and that becomes the first row. Excuse me. This is the second column and turns into the second row, and so on. So finally, I would like to talk about linear independence and a property of a matrix called its rank. So first let's talk about linear independence. So here I have this one vector here, and now I have another vector, 1, 3, and that looks like this. So now we have these two vectors. And now my question for you is, are these two vectors linearly independent? So is this a linearly independent set of vectors? The answer is yes, and this confuses people sometimes. If this is the first time you're introduced to this concept of linear independence, you might initially think that the answer is no, because you look at these vectors and you see they're related to each other. And initially, you might think that only orthogonal vectors, or only vectors that meet at right angles, can be independent of each other. But independence is not the same as orthogonality. Orthogonality is like the extreme case of independence. The question about independence is, could you get to one of these vectors by linear combinations of the other vector? So is there some way that we can scalar multiply this yellow vector and get to this blue vector? And the answer, of course, is no. There's no way we can do it, because multiplying this yellow vector by any number will only give us another vector along this line. It's never, multiplying by a single number will never change the direction of this line, and this line is pointed off in a different direction. All right, so this is a linearly independent set of vectors. So now I want to add this other vector. So now this is vector 2, 4. And now the question is this a linearly independent vector that we've added? So you can probably already guess the answer is no. The answer is no for several reasons. But the most obvious reason, which you see here geometrically, is that we can get to vector 2, 4 by taking this vector 1, 2 and just multiplying it by a scalar. So we multiply this by 2, and then we get this new vector. So this new vector, this red vector, doesn't point off in any different direction. It points in a direction, or I should say, we can perfectly reconstruct this vector purely by a linear combination of another vector. So this is not a linearly independent set of vectors here. Okay, so this is about linear independence, and so that case was sort of obvious. Now I'd like to present another case and ask the same question. Are these 3 vectors? So is this set of vectors linearly independent? Now, again, so this one is tricky. You might initially be tempted to say that these are independent vectors because they point off in different directions. And it's true that they point off in different directions, but remember the question we need to ask here is whether we can get this vector by some linear combination of these other vectors. And the answer to that question is yes, actually we can. We can reconstruct this vector based on linear combinations of these other 2 vectors. It might not seem obvious right now how we do that, but if you imagine scaling this vector negative, this yellow vector, so it comes all the way down here, and now you take this blue vector and you scale that up and you add that to the end of the yellow vector, you actually would get here. And you can confirm that here. I forget exactly offhand what the combination is, but I think it's like -9 times this vector plus 7 times this vector or something like that. And that will give you exactly this vector. So now we have a linear combination of these 2 vectors that gives us this 3rd vector. So this is not a linearly independent set of vectors. Any 2 of these vectors are linearly independent, but the 3 vectors combined is not linearly independent. All right, so that's about linear independence. So now if we take these vectors and we put them into a matrix, so it looks like this. So these are the 3 vectors, and we're putting them as column vectors into this matrix. Although that doesn't matter, we could have also made these row vectors and had a 3x2 matrix. Now we change the phrasing of the question. So we don't ask whether this matrix is linearly independent. Now we ask, what is the rank of this matrix? And the rank of a matrix is the number of columns that are linearly independent, or the number of rows that are linearly independent. So the answer here is that the rank of this matrix is 2, because the total number of linearly independent vectors here is 2. Now, this is, like I mentioned at the very beginning of this lecture, there's a lot of, or there are several sort of deeper, more theoretical reasons why the rank of this matrix has to be 2. One of them, for example, is that there's just no way to have more independent vectors than you have dimensions. So if you have a 2-dimensional space, there's no possible way to have 3 linearly independent vectors. But the rank of this matrix is 2. But the rank of this matrix is also 2. So it can seem a little weird at first, but it basically means that the rank is the number of columns that provide independent information. Now, let's take a minute to think about what this would mean with electrophysiology data. So imagine you recorded data from 64 electrodes and 10 million time points. So the question is, what is the total possible rank of our matrix? So 64 channels by 10 million time points. The answer is 64. 64 is the highest possible rank that matrix can have. And you would get a rank of 64 when each channel is measuring at least somewhat independent activity. Now, of course, there's a lot of autocorrelation, particularly with EEG or MEG data. So these channels are not uncorrelated with each other. They're very strongly correlated with each other. But they're still linearly independent of each other, so the rank is 64. Now imagine what would happen if one of the electrodes were broken. So you were only really measuring valid data from 63 electrodes, but you want to have 64 electrodes because you want to be able to compare across different subjects and so forth. So you interpolate that 64th channel, the one bad channel. So now you still have 64 channels. And what would be the rank of this matrix? The rank of this matrix would be 63, because one of those channels is a perfect linear combination of data from all the other channels. In other words, just by knowing the 63 channels and by knowing the weightings for all those 63 channels, we can perfectly reconstruct the 64th channel, the one we interpolated. So the rank would be 63. So rank is an important quality of a matrix because it tells us about what we can and cannot do with those matrices. So there are certain operations that are valid only on matrices that have full rank. So we will come back to the issue of rank in the next lectures, particularly when it comes to least squares. Oh yeah, so here was the thing about independent versus orthogonal. So here we have two independent vectors. These are independent because there's no possible way to have a linear combination of one vector that gives you the other vector. And here is a vector that is orthogonal because it meets at a right angle. And if you remember from an earlier lecture, we discussed that orthogonal vectors have a dot product of 0. So if you would compute the dot product between this vector and this vector and this vector and this vector, then you would see that the dot product between these two guys is 0, and the dot product between these two guys is not 0. Geometrically, what that means is that these two vectors, the orthogonal vectors, meet at a right angle. So this would be a right angle here. And these two vectors do not have a dot product of 0, so these are not orthogonal. They do not meet at a right angle. Again, orthogonality is not the same thing as independence. It's like, you can think of orthogonality as being the most extreme case of independence. Of course, in this case, this is not a linearly independent set of vectors. We could take any two of these vectors, that would be a linearly independent set, but the three of them together is a linearly dependent set, even though these two vectors are orthogonal to each other. Right, so let's have a look at some of this in MATLAB. Here is the bit about transposing vectors. So mostly transposing is done with the apostrophe. So we can see this is a 10 by 1 matrix, so it's a column vector. So here we see it's a nice column vector, and now we can transpose it, and now it becomes a row vector. There's also the function called transpose, which does, well, for real valued inputs, it looks like it does exactly the same thing. It's a little bit more complicated than that because this apostrophe is not only computing the transpose, it's actually computing something called the Hermitian transpose, which is only does something to complex inputs. But we don't need to worry about that so much now. But if you are going to be working with and transposing complex vectors, then it's important to know whether you're applying the Hermitian transpose or just the normal transpose. So, and again, this is not very surprising. We can transpose the transpose, and we get back to our original vector. This seems like it should be, a pretty obvious thing, but I point it out only because showing that the transpose of a transpose is the original matrix is important for some proofs in linear algebra. All right, so here we get to our three important matrices. Square matrix, well, you already know how to generate a square matrix using the rand function. You just input a single input, and it will give a square matrix of that size. So it turns out, so I'm going to talk about this in, I think, the next lecture, that one way to get a symmetric matrix is to take a normal matrix, a non-symmetric matrix, not even necessarily a square matrix, and multiply it by its transpose. So you can see it's the matrix transposed times itself. And it turns out that this is a symmetric matrix. So here we generate these three special matrices. This is the identity matrix, and that you get with this function I. Finally, we have rank. And the main point here is to show that the function for computing rank is rank, so it's well named. And you can try playing around with the rank of a bunch of different matrices. Good, so I think that's it. I hope you enjoyed this little lecture. It's a very quick introduction to important concepts, important elementary concepts in linear algebra, and we're going to continue building on these concepts to talk about least squares and eigendecomposition.